All right, welcome back to the online causal inference seminar. Today we are excited to have Yuhao Wang from Tsinghua University, who will talk about root and consistent estimators for average treatment effect with minimal sparsity. One of his collaborators, Rajen Shah, is in chat today. So if you have, is in Q&A today. So if you have any questions, please, as usual, submit them via Q&A. After that, we'll have a discussion by Rajarshi Mukherjee from Harvard University. Looking forward to that. Questions today overall will be handled by Jingwen, so I'm quickly handing over to him.
Yes, okay. As everyone knows, probably know already, please use the Q&A tab on the bottom of the Zoom to submit your questions. This will allow Rajan to answer some of the questions as Yuhao is presenting. And we can take some of the questions to a live discussion if time permits. Without further ado, I will hand over to Yuhao.
Okay, so I'm going to share my screen. Can you see the screen sharing now?
Yep, looks great.
Okay. So now I'll start my talk. Okay, thanks a lot for the introduction by Professor Dominic Hauser, and also for the organization by the online causal inference committees, especially Dominic and Qingyuan. And thanks a lot for Rajarshi to come here for Discussant, and my collaborator, and also my former postdoc advisor, Rajen Shah, for handling the Q&A. So in this talk, I'm now going to present my recent work on root and consistent estimators, my recent research on developing root and consistent estimators for the average treatment effect estimation with the minimal sparsity condition. I'm Yuhao Wang. I'm currently an assistant professor at the Institute for Interdisciplinary Information Sciences at Tsinghua University. So this is based on my joint work with Professor Rajen Shah from the University of Cambridge, and Professor Lin Liu from the Shanghai Jiao Tong University, who is also in the. I have seen that he is currently also in the attendees. Thanks for coming in. Okay. So before I talk about my research in details, let me first start with some motivating examples. In many applications, people are actually interested in, for example, understanding inferring the causal effect by manipulating usually a policy or treatment variable, and we want to know the causal effect of these manipulations on the distribution of some variable interest in the environment. Usually we call this variable as the outcome or the response variable. For example, in social science, people are usually interested in understanding what is the possible effect of attending college, on student earning. So in this case, the attending college will be the treatment variable, and the student earning is the response variable, after the treatment. In the epidemiology, people are usually interested in understanding the influence of taking vaccines on, for example, the COVID-19 infection rates. In order to answer these questions, we really need to estimate, an estimate called the average treatment effect, which represents, for example, the average causal effect of this policy or treatment variable on the entire population of interest. Okay, now we are done with introducing the motivating examples. Let me now turn to the problem set of this talk. In this talk, we consider a setting. We have collected data xi, ti, and y from I equal to 1 to n. Which is RID data that is randomly generated from some superpopulation. Here, xi is a p-dimensional vector which represents the correct features, of the individual I. And Ti could be either equal to 0 or 1 is the treatment indicator indicating whether this unit has received the treatment or not. So here Yi is the response variable. It is the Y corresponds to the observed outcome of unit I if the unit I has received the treatment Ti, which is either Ti equal to 1, which means that this unit has been treated, or Ti equal to 0, which means that this unit has been is under control. Of course, for all the attendees of this talk of this online causal inference seminar, you must know that in order to describe causality, we need to introduce some framework to describe causality, such as the causal diagram models or the potential outcome framework. So in this talk, we adopt the potential outcome framework to describe the causalities. Basically, we assume that for each unit I, there are two potential outcomes, y1 and or y0. Here y t could be equal to 0 or 1 correspond to the potential outcome of unit I if the unit I has been assigned with treatment t, which is equal to 0 or 1. Based on this framework, the relationships between the observed outcome yi and the potential outcome y1 and y0, they would satisfy the following equation that it is equal to y1 if ti is equal to 1, and it is equal to y0 if ti equal to 0. Now we are equipped with the potential outcome framework. We can define our target of interest, which is we call as the average treatment effect as the following quantity, which is the expectation on the differences between the potential outcome y1 and the potential outcome y0. And in this talk, as you can see from the title, in this talk we are primarily interested in and inferring the causal effect in the high-dimensional setting. Because for all the attendees in this talk, you must know that for this seminar, you must know that usually the causal effect is usually not identifiable unless we impose some causal assumptions on data. So here we consider the unconfoundedness assumption that the potential outcomes y1 and y0, they are conditionally independent from the treatment assignment ti by giving the xi. And we also consider the high-dimensional setting where the dimension of coerced xi p actually can go to infinity as the number of sample sets go to infinity. Okay, in this setting, a classical approach, to estimate the average treatment effect must be the augmented inverse propensity rating estimator, which is developed by James Robbins and his collaborators, including Andreas Rudnitsky. And it is further developed, extended into the double machine learning approach by Professor Viktor Zhunzhukov from MIT and his collaborators in the 2018, and they can be used to estimate average treatment effect. Basically, these are two-step procedures to estimate the average treatment effect. The first is to estimate nuisance functions, such that one is called propensity score model, which is the probability that the xi has been assigned with treatment group, which means that ti equal to 1 given the correct vector x, and the outcome regression model, which is the conditional expectation of the response variable in the treatment group or in the control group. After we have estimated the pi x and the rtx, which we use r hat and pi hat, to denote their estimate, we take this estimate as a plug-in to some m estimator to estimate the average treatment effect. So in the high-dimensional setting, when the outcome regression models are T or the probability score model, the pi x, they follow some sparse generalized linear models, such as the outcome regression model and probability score model. We assume that they can be expressed in the following form with link function psi and phi, and with some coefficient beta t and gamma. And we further use SR and S pi to denote the sparsity of the beta and gamma. So here the sparsity means number of non-zero entries in the parameters. In this case, using some standard results in the high-dimensional literature, so especially high-dimensional literature for the generalized linear models, we can prove that actually in order to estimate the average treatment effect in the 1 over square root n rate, which we usually call it square root n consistency. So this kind of DIPW or double machine learning based approach usually require that the sparsity of SR and S pi must satisfy the following equation, that the SR times S pi must be of small order of n over log p square. After this result, of course, this is a standard result. Recently, there has also been some extensions to further relax this sparsity results, such as the paper by Inanna Burdick and also Stefan, who is the organizer of this talk, and Yinchu Zhu. So they have proposed a new method that can achieve the square root consistency, and of course it is also unbiased and asymptotic normal when the sparsity of the outcome regression model is of order square root n over log p, and the probability score model is of order n over log p, or that the outcome regression model is of order n with power 3 over 4 over log p, and the probability score model is of order square root n over log p. So this is more relaxed than the previous sparsity condition. And there is also research by Professor Anthony and her collaborators. They have proposed research that can achieve the square root consistency when the outcome regression model is of order square root over log p, and the propensity score model can actually be arbitrarily complex. For example, pi can be a non-parametric model, or maybe can be completely misspecified, or it can be not very complex such that it cannot be consistently estimated. It doesn't matter. So as long as the outcome regression model has sparsity of order square root n over log p, their approach is guaranteed to get square root n consistency. In another research proposed by Inanna Burdick, they also studied some necessary conditions on the square root and on developing square root consistent estimators for the semiparametric estimation, including the average effect and also other semiparametric problems. All of this research, including the research by different researchers, I think that they suggest that the following condition might be sufficient and necessary for the square root consistent estimation. And in this talk, we call it minimal sparsity. So basically, we conjecture that we can develop an estimator that to achieve the square root consistent estimation of treatment effect, when either that the outcome regression model is sparse model with sparsity of order square root n over log p, and the propensity score model can be arbitrarily complex, or that the propensity score model is of order square root n over log p, and the outcome regression model can be arbitrarily complex. In other words, we want to design estimator that is square root consistent when just one of the nuisance functions to be a sparse model with this sparsity constraint, and the other model can be arbitrarily complex or can be very hard to estimate. In addition to this, we want our model, our estimator to be model agnostic, in the sense that this estimator just know that there is one noise function that is a sparse function, but it does not know which one it is, and it can still give the square root n consistent result. In other words, we want our estimator to be we want it such that our estimator does not need to know the identity of the sparse noise function. So this is the goal we want to achieve. To our knowledge, this is also the biggest sparsity condition that has been studied in the high-dimensional average treatment effect estimation literature. Below, of course, our paper is not the first paper to study or to try to understand this minimal sparsity condition. Previously, there are also some previous research that is trying to study some similar problem. Of course, one of the relevant literature is the research done by Professor Lin Liu and her collaborators, which can get a square root consistency, when the outcome regression model is a sparse model, and the propensity score model can be arbitrarily complex. However, in the other case, that the propensity score model is a sparse model and outcome regression model is arbitrarily complex, their paper does not have any theoretical guarantee. In a recent research proposed by Viktor Chernozhukov and I think Rahul Singh is also here, who is also in the attendance as far as I can see. So thanks for coming, by the way. So they also have proposed square root consistent estimators with the minimal sparsity constraint, but with the additional constraint that coefficient for the outcome regression model and the error random of the coefficient of the outcome regression model and the propensity score model must be bounded below by a constant. In other words, they require that they must have bounded error random. So in the setting that one of the nuisance function is a dense model with many a dense model with many small entries, this may be difficult to be satisfied. And there are also some some recent research by Smucker and Zhiqian, and also Yin Yang, and also Stingeman, Stilland, and their collaborators. They have proposed square root inconsistent estimators for the average treatment effect with just one sparse noise function and sparsity of order square root of over log p. However, they still require some kind of estimability assumptions on the dense model or on the non-parametric model. For example, in research by Zhiqian Tan, in addition to requiring that one of the noise function to be a sparse model, they also require some sparsity assumptions on the projection of the non-parametric noise function. So in other words, they still require some. And also in the research by Smucker and the other people, they also have similar properties that they require some assumptions on the non-parametric model or on the mixed specified model. Based on this previous research, we have proposed two consecutive works to tackle the minimal sparsity problem. The first approach is the debiased inverse propensity calibrating estimator, which was done by me and Professor Rajen Shah in the 2020. Basically, we can prove that it is square root consistent when the outcome regression model is arbitrarily complex and the sparsity of the propensity score model is square root over log p. In other words, it is complementary to the research by Susan, Professor Susan essay. Of course, by the time it was published, we think that it is an important breakthrough, compared to the previous research. However, it still did not fully, and we think that it has partially tackled this minimal sparsity problem. However, it still did not fully solve the minimal sparsity problem. As an extension, very recently, under collaboration with Professor Lin Liu from Shanghai Jiao Tong University, we further extended it into the double calibration estimator, which is, and we prove that it is square root inconsistent just with the minimal sparsity condition. In other words, it is model agnostic in the sense that it just need to know that one of the noise functions is sparse model with the sparsity constraint. However, it does not need to know which one is sparse model and which one is not. As an extension, we further extend it into the to develop square root inconsistent estimators for the regression coefficient estimation with minimal sparsity. And another thing is that in both the DIPW research and also the research by Professor Susan essay, so they only consider the exact sparsity case in the sense that one of the nuisance functions must be exactly sparse. We further extended it into the proximate sparsity case in the sense that we can get square root inconsistency when one of the noises function is approximately sparse and the other can be arbitrarily complex. Okay, now I'm done with a general overview of the previous research and a brief introduction of our main contribution. Now I'm going to talk about the two estimators in detail. Okay, the first part is a part one, which is I'm going to introduce the debiased inverse propensity score weighting estimator for square root inconsistent estimation of average treatment effect with a sparse propensity score model and arbitrarily complex outcome regression model. So this is based on my joint work with Professor Rajen Shah from the University of Cambridge. Before I talk about our method in detail, let me first start with the inverse propensity score weighting estimator, which is also the estimator that motivated our research. Recall that for the IPW estimator, so in order to get the of course it's not square root consistency. In order to get a consistent estimation, it does not require estimating the outcome regression model. In other words, to get all the desired properties of the IPW estimator, the outcome regression model can be arbitrarily complex, which is just like our method. However, a major issue of IPW is that the biasness of IPW is usually much larger than 1/√n rate when we are given a high-dimensional model with sparsity of order the probability score model of order √n over log p, which is the main challenge we want to solve. So as we can see that the main challenge for IPW estimator is the large biasness in the estimate. That's why we call our estimator as the debiased inverse probability score weighting estimator, where we have introduced mu. Mu is an n-dimensional vector from 1 = 1 to n in order to reduce the biasness of the original IPW estimator. So here we strip all the y's with mu I in the hope that this mu I can reduce the biasness of the original IPW estimator. Of course, after from here, it will be interesting to make a connection, with the original AIPW connection with the AIPW estimator, which also can achieve the √n consistency. In fact, based on some transformations which we have mentioned clearly in the paper, which you can read by yourself. Actually, AIPW estimator can actually be rewritten in the following form. So you can see that it has similar form as the DIPW estimator here, except that for the mu s, mu s is and also with mu s that is expressed as a function of the probability score model and the function of the estimated probability score model and the estimated outcome regression model. In other words, compared with the DIPW estimator, we can view AIPW estimator as that it constructs the mu hat, by estimating the outcome regression models RT and the probability score model pi separately, and combining them together to construct mu hat. As we'll show later, in DIPW estimator, we construct mu hat for debiasing based on the directions of the errors of the probability score model estimation. And we have found that it is very useful when the outcome regression model RT is not estimable. Okay, now I'm going to provide some step-by-step analysis to showcase, how the mu s can be used for debiasing. Assuming by design that we generate mu I in a way such that the mu s and TS, they are conditionally independent given the correct matrix X. In this case, we can have that the following oracle estimator, where we have replaced the estimated propensity score pi hat with the true propensity pi. This estimator is actually unbiased, to estimate how. This is because if we forget about the mu's here, we just consider the y's, then it becomes the oracle IPW estimator, and we can already prove that it is actually unbiased to estimate arbitrary effect. This means that we only need to show that the following term is unbiased. The limited term is just involves mu. Now we first do a transformation. We first do a conditional explanation of this term by conditioning on the correct matrix X, and we take an expedition afterwards. Then using that the mu s and TS, they are actually conditionally independent from each other by giving the X. We can have that this is equal to the following expression. And apparently, for the conditional expedition of Ti given X, it is actually equal to pi, and the same here. So we can further rewrite it as the differences of the expedition of mu minus itself, which is equal to 0. So this shows that at least this oracle estimator with the oracle probability score model, it is unbiased. In this case, in order to understand the biasness of DIPW, we only need to understand the differences between DIPW and this oracle version. And by doing some transformation, we can have that it is actually approximately equal to the following thing. So which is the prediction area of the pi hat minus pi times some term, some term which is function of pi of yi and also mu I. By further assuming that the propensity score model follows a logistic model, and by manipulating the about term, which and we will discuss this further, in the following slides that about the logistic model thing. And by manipulating the about term by using Taylor expansion and Holder's inequality and some other technicalities, we can further have that some totally the biasness of the DIPW estimator is actually upper bounded by the following term, which is, as we can see, it is a product of the two terms. One of the term is the error norm of gamma hat minus gamma, which is the error norm of the estimation errors of the logistic regression coefficient. Usually it is of order s pi times the square root of log p over n. And the second term is actually the L infinity norm on the differences between these two terms. One of the term is called x transport times mu, and the other term is x transport times y tilde. So y tilde is an n-dimensional vector where the ith entry is can be expressed as the following thing. Of course, you do not need to understand this expression exactly, so you can just take it as a function of ti y and the pi hat I. So, and that's all. Now, if you can choose mu such that the R infinite norm on the differences between these two vectors is of order square root of log p over n, then we can have that the biasness in A is of order s pi times log p over n, which of order small order of 1 over root n. If pi is of order square root n over log p, and this can solve the biasness of in the A. However, actually, it turns out that we cannot choose mu by solving this R infinite norm directly. This is because if we choose mu by directly controlling this R infinite norm to be of order square root of log p over n, then the requirement that the TR and the mu-s, they are conditionally independent from each other, conditioning on the x, this cannot be satisfied anymore. In order to fix this issue in this estimator, we consider the case that we have some auxiliary sample xa, y, and ta that is equal in distribution, that is independent from the xyt, and it is equal in distribution with the main data set xyt. Of course, in practice you can create by the sample splitting. And we instead of seeking the mu that can satisfy this constraint, we seek mu that can satisfy the following alternative constraint. You can say, as we can say, this is the same as the one in equation 1, except that we have replaced the x transport from y tilde to the xa transport times y tilde a. Now using sub-Gaussianity, now the mu can already satisfy this R infinity constraint. And by assuming further assuming that the x is a sub-Gaussian vector and the potential outcome yt is a sub-Gaussian random variable, we can further have that the R infinity norm on the difference between x transpose a times y tilde a and x transpose times y tilde is also of order square root of log n over p, log p over n. And then by taking together, we can have that once we can use mu to satisfy this constraint, this can satisfy the R infinite norm on the equation 1 as well. And because in the generation of the mu, we only use the x in the main data set. So this means that we can still maintain that the TR and the mu-i, they are conditionally independent from each other by given the x. Of course, notice that by finding a mu that can satisfy this constraint, that this R infinity norm is of order square root of log P over n. This does not require the outcome regression model to be estimable, or does not require this can be estimated with any rate, convergence rate. Instead, it just requires the sub-Gaussian entity of x and yt. So this means that our DIPW estimator can reduce the biasness without imposing any assumptions on the, for example, estimability or the complexity of the outcome regression model. Okay, we are showing that how the mules can be used to reduce the biasness. Now I'm going to show that. Now I'm going to discuss the variance control of introduced mule. Because here, as there are many mules that can satisfy this R infinity constraint, that this is of R is bounded below by square root of log P over n. We may want to choose the mule that can reduce the asymptotic variances of the DIPW estimator. Of course, there are many ways to reduce the variances, and so a naive way is to choose by minimizing the L2 norm. So which gave us the following program. Here we minimize the L2 norm of mule. We want to take mule hat that can minimize the L2 norm under the constraint that the R infinity norm is bounded by eta. Of course, in practice, we can choose eta to be the same order of magnitude as the square root of log P over n. And we can prove that as we will show in our paper, we can prove that once we choose mule with by solving the following program, we can prove that the variances of the DIPW estimator, which is of order 1 over n, so which prove the square root n consistency. Yeah. Okay, now in order to further get a asymptotic variance that is smaller than, for example, the one given by the equation 2, we can further change the coordinate program as the following thing. So here you can see that it is the same as before, except that we introduce another function mu tilde. So mu tilde is an approximation of the conditional expression of y tilde that is constructed from the auxiliary sample. Of course, here are a few remarks I would like to emphasize, in this construction. Firstly, that the primary goal of introducing the y tilde is to reduce, for example, the variances of the DIPW estimator by a constant order. Of course, and also, so y tilde, does not necessarily need to consistently estimate the conditional expression of y tilde, given x, in order to achieve square root consistency. For example, one can simply set y mu tilde to be always equal to 0, and this breaks down to the following program, and we can still prove all the desired properties. So. And the primary reason to introduce my tilde in this program is that we have found that it can improve the empirical performance, especially when the mu tilde is not, even if it is not a consistent estimation of the y tilde, but it's for example it's kind of closer than without using it. It can it can reduce the variances. Okay. In sum, we can introduce the following procedure to estimate the error treatment effect. The first is that given a whole data set of size big N, we first split in 3 parts, which is the first part is D and DA and DB. Firstly, that we can use DB, to estimate the propensity score model pi hat and also the mu tilde function. And second, that we can use the D and the DA to construct an estimation of the mu hat. And third step, we take both mu hat and the pi hat as plug into some M estimator that is based on the average of the dataset D to estimate error treatment effect. Okay, using the following 3 procedures, we have the following theorem. which is that under standard regularity conditions, and assume further that the propensity score model follows a logistic model with sparsity of order square root n over log p. We have that the mu hat, the estimation errors of the DIPW to actually the top bar, which is the sample error tripping effect of all the units in the main set D, by conditioning on the correct vector x and dA and dB. It is asymptotically it is normal random variable with the following variance. Here the sigma bar is so actually this variance has two components. The first is sigma bar or sigma bar square. It is actually the ideal variance. It is actually the ideal variance, for example, for the DIPW estimator. If, for example, we are instead of given some kind of oracle motion or some very powerful motion, of course this is not realistic, but you can imagine a setting where we are given some very powerful motion and some additional data, such that the outcome regression model can be estimated with high accuracy. In this case, in this case, we can take sigma bar as the ideal variance that can be possibly achieved by any estimator, such as DIPW. The ideal variance is that it can be possibly achieved by any estimator. In this case, the sigma mu is actually a variance inflation, of our DIPW estimator by introducing the mu hat. And we have proven that with probability 1, conversion to 1, it is of order 1. This means that the DIPW estimator actually reduce the biasness as a cause of reduce the biasness. DIPW estimator actually increase the variances with constant order. Okay, so far we have proven that we are showing that how the DIPW estimator actually reduce the variances make the debiasing, and as a cost, it may increase the variances by a constant order. And of course, it will be interesting to understand under what conditions the DIPW estimator is not only square root consistent, but it is also semi-parametric efficient. And we have the following theorem. If in addition to the previous theoretical guarantees, we can have that in addition, the outcome regression model can be estimated with convergence rate of order 1 over square root of log n. Then by using the cross-fitting, namely that we change rules of dA, dB, and D, and do this again, and then take the average, which we usually call as cross-fitting, which is cross-fitting. And by making some other modifications of the DIPW estimator that I shown before, we can prove that the DIPW estimator is actually simply normal to estimate the true average trimming effect. Moreover, the variance is sigma is actually the semi-parametric efficient variance of the average trimming effect estimation. Of course, notice here we see that the additional assumption that outcome regression model can be estimated with convergence rate of order 1 over square root of log n. We are so actually here the outcome regression model can be non-parametric. For example, you can use the high-dimensional linear models, or maybe such as lasso, or you can use the random forest, for the high-dimensional models which was being developed recently. Doesn't matter as long or even kernel method. If you find a good kernel, it doesn't matter as long as the convergence rate is of order 1 over square root of log n. Then this result will still hold. And we believe that the convergence rate that 1 over square root of log n is actually a very mild conditions on the outcome regression model. Okay, so far all the results are based on the assumption that the propensity score model is not only a generalized linear model, it is also a logistic regression model. We now discuss some extensions with other link functions. So when the phi is not a logistic regression model, but instead it is some other link function with the bounded, uniformly bounded first order and second order derivative, we can modify the quadratic program as following then. So here, as we can see, it is the same as before, except that we multiply, the X transpose and mu with a diagonal matrix pi. So pi is a diagonal matrix such that its RS entry is equal to phi prime of X transpose times gamma hat divided by pi hat I times 1 minus pi hat I. So and using this program, using exactly the same proof as before, we can still prove that DIPW is square root consistent estimator. Okay, how much minute am I left?
Around 5 or 6.
Okay, okay.
Thanks.
Okay, so I will go over very quickly. So I mean, not into numerical studies, we also compared our method with the other state of the art method, for both arbitrary effect estimation and also for the estimation of the variances. Also for the estimation of the variances of the potential outcome y1, with different sparsity with different sparsity on the propensity score model from 5 to 50. So we can say that our method, can consistently outperform the other approaches, even for relatively dense models. Okay, now I'm going to turn to the second part, which is double calibration estimator for the square root consistent estimation with the minimal sparsity condition. So this is based on my joint work with Professor Lin Liu from the Shanghai Jiao Tong University. Recall that for the DIPW estimator, so we introduce mu hat for the debiasing. From the calibration perspective, we can view mu hat as a calibration of the outcome regression model based on the direction of the propensity score model estimation error. In other words, we can view DIPW as a calibration-based approach where they estimate error changing effect by a single calibration. In other words, to achieve the minimal sparsity, namely that we want our estimator to be square root n consistent whenever either the outcome regression model is sparse or that propensity score is sparse, then intuitive idea is that we want to calibrate propensity score model as well. So this results in the double calibration approach, where we instead of using the pi hat in the estimator, we replace it with some pi tilde, which is defined as phi times the X transpose times gamma tilde. So here, gamma tilde is constructed by solving some specific automation program that is designed, for the calibration. So here, in other words, in the double calibration approach, we introduce mu hat for the outcome regression model calibration based on the direction of the propensity score estimation error, and we use the gamma tilde for the propensity score calibration based on the direction of the outcome regression model estimation error. Of course, because I'm already introduced a lot of math, in this talk, I'm not going to go over the math details of the double calibration approach. But if you are interested, you can look at our draft on the archive. So now I'm going directly into the theoretical analysis. Just like the DIPW approach, we still split, the entirety of the set into D and DA and DB. And then we want to estimate for example, the sample average effect on the main data set. We now have the following guarantee. First is that if the outcome regression model follows a sparse generalized linear model with sparsity of order over log p, then by conditioning on the X and T on the main data set, as well as D and DB, it will be a simply normal estimator with variance depending on the XT and the D and DB. If other words, the propensity score model follows sparse general linear model with sparsity of order n, or the the square root of log p times the maximum of p and n, we can still have that this double calibration estimator is a simply normal estimator, but by not exactly, it's a conditional simply normal estimator, but actually conditioning on different data set. So here you can see that we still need to condition on D and DB, but actually we conditioning on the X, not on the X and T. And also the expression of the variances is also depending on X, D, and DB. Now, and the expression is actually different from the outcome regression model case. In other words, we have proven that the double calibration estimator is a square root consistent estimator with just one sparse noise function. However, with actually with different kinds of sparsity, the distribution of the double calibration estimator could be quite different actually. It's actually different. Okay, now I'm further going to discuss some extent, and also what is interesting is that in order to get square root consistency, we actually require sparsity to be of the following form. When the p is in the same order of magnitude as n, or it is n with some power, it is exactly the same as the minimal sparsity. However, for example, when the p is much smaller than n, such as the log of n, then it is it is slightly stronger than the minimal sparsity by logarithm square root of logarithm, which is another interesting phenomenon I want to share with you. Okay, so we now turn to the extension to regression coefficient estimation. So here for the problem setup, we consider the setting where y is equal to t times some coefficient tau, which is the touch of interest, plus some r of x, which is a function of x, plus some random noise epsilon. And t is actually a function of x plus some noise. So here t can be continuous random variable, does not need to be a binary variable. And our touch of interest is actually the regression coefficient tau. Then by generalizing the proof in the double calibration approach for the ATE case, we can prove that if either the R function or the pi function is a sparse generalized linear model with sparsity of order square root n over log p, or the sparsity of order square root n over the log p times log p. Sorry, there's table here, actually the maximum of n. Maximum of n. So if we have this case, of course, here we just assume one of the noise function R or pi to be a sparse model, and the other one can be absolutely complex. Then we can still have that the double calibration estimator for the regression coefficient is square root consistent estimator for the regression coefficient tau. In summary, in this talk, we have presented the DIPW estimator, and we prove that it is square root consistent just with the propensity score model following a sparse generalized linear model, and the outcome regression model can be absolutely complex. As an extension, we further propose the double calibration estimator, and we prove that it is square root consistent under the weaker, the minimal sparsity condition, that just one of the noise function need to be sparse, and the other can be absolutely complex. And for the mathematical completeness, and by adapting the proof by Elena Braddock and her collaborators for the approximate linear noise functions, we further prove that this minimal sparsity condition is indeed a necessary condition for square root consistent estimation with sparse generalized linear models. And we think that it has opened many questions. For example, what if one is arbitrarily complex model and another is dense model, namely that the sparsity is much larger than the square root, then what would happen? Now, this has been studied, for example, for the high-dimensional testings in the quadratic functionals, as far as I can remember, because I was involved in some of this research before. But I think that this still missing, for example, for the general functionals such as the arithmetic effect, or maybe maybe some other functionals of interest in the semiparametric learning. Okay, thank you very much for listening, and for more details, please see our papers on the archive. Okay.
Thank you, Yuhao, for the great talk. So Rajan has answered most of the questions from Q&A, and without further ado, let's have Rajarshi give his discussion first. And if there are more questions coming up, we can discuss them at the end.
Okay, let me share my screen. Can you guys see my screen?
Yeah.
Okay. Thank you so much first to the organizers for inviting me for the discussion. And thank you, Yuhao, for a wonderful talk, and congratulations on some really exciting results. You are answering really open gaps in the literature at this moment and the necessity of sparsity on different nuisance functions for functional estimation. So to initiate the discussion, what I'd like to do is recall the setup that we were in. So we have data, IID data from an outcome Y, a treatment or exposure T, which is binary, and baseline confounders X, which is P dimensions. Their joint distribution is some distribution P coming from some model script P. And the quantity of interest we want to understand is this notion of causal effect of T on Y. And one summary of it, namely the average treatment effect, which is the difference of the counterfactual means between the treated and the not treated. And as Yuhao pointed out, like under some standard assumptions, one can identify this average treatment effect from the data generating distribution as the quantity at the bottom of the slide in red, which we denote by tau, which is just the expected value of the Y among the treated, conditional on X, minus the expected value Y among the not treated, conditional on X, and then marginalized over X. And the traditional goals in literature can broadly be divided into two aspects. One line of literature focuses on what one can refer to as consistent and asymptotically normal estimation, so which can be further broken down into following three pieces. First piece is like, how can I get an estimated tau hat of tau so that no matter what my P in my model space is, the difference between tau hat and the truth is order 1 over root n. Once you can guarantee that, one might want to know that if I scale the difference of tau hat minus tau with root n, do we have an asymptotic distribution? And hopefully it goes to a normal distribution with mean 0 and some variance sigma squared. And once we have that, then we can start asking is like, what is the best possible sigma squared P? What is the smallest possible one? And in classical statistics, when the dimension of the problem is fixed, this is known as efficiency. So that's one line of research, which is like a point-wise understanding of the problem and constructing confidence intervals and rate consistent estimator at every point of a model. One can parallelly ask what one can think about is the minimax rate optimal question. It's like uniformly over all distributions in my model, what is the best estimator which minimizes the mean squared error between the truth and the quantity of interest? And in this case, one tries to find a sequence of real numbers, Rn, that goes to 0, and this will be a function of the model class script P, such that my minimax error of estimating tau with some tau tilde scales like Rn squared P in mean squared error set. So the kind of models people have dealt with in practice, the two popular regimes can depend on dimension. So when the dimension of the problem P is fixed, then the script P model class often classically dealt with parametric problems, where you posit parametric models for nuisance functions like outcome regression and propensity score. And people have also worked a lot on non-parametric smoothness classes for nuisance functions. In contrary, for the large P setting, which was the focus of Yuhao's talk today, the script P typically corresponds to sparsity depth classes for outcome regression and propensity score. And today's talk especially was trying to understand the can estimation question when the dimension of the problem is growing with the sample size under sparsity of the outcome regression, which I'll denote by R star T of X, which is expected value of Y given T equal to small t and X, and the propensity score pi star, which is just the chance of getting a treatment at every level of the covariance. And the dimension of the problem is typically at least as large as n, or at least grows with n. That was the focus of the talk. And the contribution of this talk is trying to understand what is the minimal sparsity one can hope for, or at least try to understand the minimal levels of sparsity in the outcome regression propensity score when one assumes generalized linear models for the outcome regression propensity score. So it really complements the literature that people have been working on a lot in the last decade or so, where previously people have either tried to understand when both the outcome regression propensity score are sparse, or at least one of them is sparse, but the other one has some kind of sparse projection, as you have said. As with any great piece of work, these two papers by Yuhao and co-authors raises very interesting future questions, which I'd like to discuss a little bit and hopefully get some answers. So if I understand correctly, the bigger motivation of the sequence of papers is trying to understand maybe a necessary and sufficient condition for some levels of good estimation for average frequent effects. So let's try to do a little bit of recap of what people have understood in this framework for fixed dimensions, but in a non-parametric class of problems. In this case, if someone assumes that the outcome regression has beta many derivatives as a function of x, and the propensity score has theta many derivatives as a function of x, then in 2009, Jamie Robbins, Ling Li, Eric Chegin, and Art Vanderwaart proved that CAN estimation is possible if and only if the average smoothness of the outcome regression propensity score is above the dimension by 4. Not only that, if the average smoothness of the outcome regression propensity score follows below the dimension by 4, you can no longer get root n consistent estimation, and the mean squared error of estimation in the minimax sense falls below root n, 1 over n, and is given by this quantity in the second bullet point of the slide. So my first question is there any hope of getting a similar sort of results when trying to do sparse regressions on the outcome regression propensity score? For example, if I assume that outcome regression is a linear regression, which coefficients beta, and the propensity score is a logistic regression with coefficient theta, and suppose I assume that the outcome regression parameter is SR sparse and the propensity score theta is phi sparse, then what hope do we have in trying to understand, like, what are the different regimes of convergence? When can we get root n rates of convergence and when we cannot? I was going to the very nice paper which Yuhao and Lin put on archive yesterday, but they had some kind of lower bound in trying to understand some kind of necessary conditions of sparsity. But if I understand correctly, the lower bound depends on simple versus complex hypothesis testing, where one tries to understand whether one can test whether the theta parameter is 0 or not. On the other hand, in Robbins et al. Paper 2009, it was shown that one actually needs to understand a composite versus composite hypothesis testing problem to paint the whole picture of minimax rates of convergence in this. So that's one question: what's the hope of getting this full picture of results? And on the second level, can at least one analyze the debiased propensity score or debiased double calibrated estimator when the assumptions on the sparsity are not met for root n consistent estimation? So that's my first question in this regard. My second question is requires a little bit of background on the actual even necessity of sparsity in some of these problems. So this I'll divide into two pieces based on the dimension being larger than n or smaller than n. So let's think about the very, very simple toy problem where the dimension of the problem is less than n, and your outcome regression is a linear regression. So y is some t times alpha plus x beta plus epsilon, where t is a vector of all the exposure variables collected over n individuals. And suppose x follows a normal zero identity in p dimension. This can be generalized, but to keep discussion simple, we can think about that. And suppose the treatment t given the covariance x follows logistic regression with theta transpose x as the parameter. And suppose the dimension p over n goes to a constant eta, which is between 0 and 1, because I've assumed p is less than n. In this case, one can think about three classical estimators that people have studied in the late 80s and early 90s. The one is the propensity score that you have already introduced, and we know it is biased in this case. But if one looks at the AIPW estimator, which is the popularly now known as the double debiased estimator, and look at the cross-fit version of the problem, that is, you estimate the outcome regression from one split of the sample, the propensity score from another split, plug it in a third split, and then do all possible permutations and average of this process, then one can show that this cross-fit AIPW estimator minus the truth scaled by root n actually goes to a normal distribution with mean 0 and some variance. And the variance actually is bigger than the classical efficient variance. And this will be true as long as you can estimate the outcome regression unbiasedly through ordinary least squares, and that is where we need p less than n. On the other hand, if we don't care about AIPW or propensity score based estimator, you can just do an outcome regression based estimator, and just using standard random matrix theory, you can show that after scaling by root n, this estimator has a normal limit with mean 0 and variance actually 1 over 1 minus eta, where eta is the aspect ratio P over n. So that's what happens for P less than n when you assume a little bit of distribution assumptions on the marginal covariance. One can try to do this a little more for P bigger than n as well. And I just tried to do a back of the page calculation yesterday. And so bear with me on this slide a little bit. So it's a very similar setup as the last slide. So it's the same distribution of y given t and x. The distribution of t and x is the same. But now the dimension P is bigger than n. So you can no longer estimate your outcome regression by ordinary least squares. But you can do just a ridge regression. And then you can hope to debias it. And if you know that some knowledge of the distribution of x, which we assumed here to be normal zero identity, then it turns out you can debias it. And I have done a little bit of very simple problem here. It turns out that the conditional bias of your ridge regularized estimator for estimating this coefficient alpha can be written as this gamma, which is the concatenation of this alpha and the beta parameters, times some matrix sigma, an explicit matrix sigma, which depends on the theta parameter, and the aspect ratio eta, and this kappa parameter, which is the ratio of the regularization lambda by n. So, and the point is, if you can correct this bias, then we are in game. We can correct the bias of the outcome regression-based method. And here's a very simple case where actually the propensity score is kind of sparse. So suppose only the first coordinate of theta is non-zero. Then it turns out that the sigma matrix is some constant, known constant, times identity. So you can then easily debias it using this inverse of this constant. It doesn't necessarily need this theta to be sparse, as long as the t given x only depends on a few coordinates of x. You can do a very similar debiasing. You do not need to assume an explicit formula for the regression function. So long story short, if you assume a little bit on the variance covariance matrix of t and x, not knowing the full distribution of t and x, t given x, then you can do this kind of debiasing without any sparsity, even for p bigger than n in the proportional asymptotic regime. So my questions will be, do we actually need sparsity, at least when the p and n are comparable in dimensions, if we assume a little bit of extra on the dimension, on the distribution of covariance? As we saw, you can potentially debias ridge regularized outcome regression. I think you can also debias propensity score-based method, but I think it's a little bit harder in this regime. We saw the DIPW estimator is unbiased if p is less than n, if you use an unbiased outcome regression estimator. So my question is, can one analyze the debiased propensity score estimator as suggested by Yuhao and Rajen Shah, and also a doubly calibrated estimator as suggested by Yuhao and Lin? And whether when we think about minimal sparsity, should we only think about sparsity or also some knowledge about the distribution of x, whether they should come together or not when we think about minimal sparsity? So that's my second question. My third question, I'll just keep it as general as possible, and we might not have time to answer them, is related to the general class of double robust functionals, which you have briefly talked about in the very beginning of the talk. So average treatment effect falls in this big class of double robust functionals, which depend on two nuisance functions. And the goal is, how can we estimate at least one of the nuisance functions well to get eventual root-n consistent estimation of this functional? There are other functionals like this, like mean estimation in missing data problem, average treatment on the treated, and so on and so forth. And the question is, how can one systematically think of extending this very exciting results that you have obtained to the general class of double robust functions? So with that, I'll end my discussion and really thank you for a wonderful talk. And once again, thanks to the organizer for inviting.
Yeah, thank you, Rajarshi, for the great discussion. We're a bit over time, but maybe if you could take 1 or 2 minutes to quickly respond to some of Rajarshi's question, and then I'll wrap.
Yeah, this is a quite tough question. I think any question, all the questions need to be answered with long time. Okay, I'm joking. So okay, let me first turn to question 2. So yeah, of course, I think this is a very good question. So I'm just yeah, it's a very good question. So that's why I need a long time to answer. So first, firstly is for example, the sparsity assumptions, when we have some information on the distribution of x. In fact, it is quite similar to the higher order infinite functions, and that because higher infinite function, as far I'm not very familiar with literature, but as far as I can understand, they are trying to estimate some some distribution of x and uses and develop some higher infinite function to do the debiasing. So So I think that this higher order Newton function literature, this can be useful, to answer the question. Yeah, sorry, can you move to the picture? So you can move to the.
Sorry. My bad. I changed my screen.
Yeah. So I think that if we dig more carefully into the higher literature on higher Newton functions, then we can propose some kind of new method to leverage, both the higher order Newton functions and the debiased approach in double calibration and the DIPW estimator to get some new sparsity result. I think it will be interesting direction to explore in the future. And also, I think that major issue is that Rajarshi can move to the previous slide.
In this one.
The question, the slide before question 2.
Oh, this one. Yeah.
Yeah, as you can see that in this slide, all of these models are under some constant effect assumption that there is no heterogeneity between for each individual treatment. So I think that but in our analysis we have found that the heterogeneous treatment effect is the main challenge to solve in order to develop square root and consistency. This is my another feeling, how we can solve these heterogeneity problems, is to get all these properties. So in other words, I think that to answer question 2, I think it would be helpful. I think that some result in the higher order infinite functions and the calibration together, can answer this question. And and now I'm going to question number 3. Yeah. So this is also a very interesting question. Actually, Professor Lin Liu and I have been trying to give some generic representations of what kind of functionals can actually be used using double calibration approach. Because now we just have 2 cases, arbitrarily effect and regression coefficient, and we are trying to give some representations of what kind of functionals can be used for double calibration approaches. And we will let you know after this is done. Yeah, I'm not sure if this has fully answered your question 2 and 3.
Yeah, I think I have to cut the discussion here, at least the formal part of the seminar. I'd like to thank Yuhao and Rajarshi again for the great talk and discussion. Next week, we have Elizabeth Rose Maeda from UCLA in our seminar. I look forward to seeing everyone there.